Hi guys, welcome to this video, where I'll be going through the whole of electricity theory as per OCR Physics A specification and using their textbook as a guide. Now this can be used for other exam boards as well, but please make sure you check the respective specifications for more clarity. And basically I've split this up into 3 sections, and let's dive into this video with section 1. In section 1, we are aiming to be able to demonstrate knowledge, understanding and application of current and electric charge, flow of charges in metals and electrolytes, conventional versus actual flow of current, Kirchhoff's first law, classification of materials, and mean drift velocity. What is current? Well, current, as you know from GCSEs, it's simply the rate of flow of charges, where delta I equals delta Q over delta T. I, Q, and T are current, charge, and time. And 1 amp of current represents 1 coulomb of charge flowing in 1 second. That is, 1 amp equals 1 coulomb per second. Electric charge is just a physical quantity, like distance, mass, temperature, etc. And the charge on one electron or a proton has a magnitude of 1.6 times 10 to the minus 19 coulombs. This is known as elementary charge and is referred to as E. Now, protons and electrons have a relative charge of +1 and -1 respectively, as their charges are compared against this elementary charge. And ions also have relative charges. So for example, copper 2 plus ion will have a charge of 3.2 times 10 to the power of minus 19 coulombs. What is net charge? It is an overall charge on a particle due to the gain or loss of electrons. And the net charge on a particle Q is given by Q equals plus or minus Ne, where N is the number of electrons and E is the elementary charge. And with this formula, you have to be careful because first, it isn't given to you in the exam booklet, so I highly recommend you learn it. And let's have a look at different charge carriers. Now, in metals, you know that the charge carriers are the delocalized electrons, which are happy to move in around a fixed lattice of ions. Now, they move randomly until the metal is connected in a circuit, and then they will align themselves once they are connected, and they will move from the negative towards the positive terminal of a cell or a battery. But as for the electrolytes, the ions are the responsible charge carriers. The positive ions will be attracted towards the negative electrode, which is called the cathode, and the negative ions are attracted towards the anode. Now, you have heard of this in GCSE chemistry. Electrolytes are simply the molten or aqueous ionic compounds. We won't be using them in electricity. In physics, however, it's still worth knowing what they are, because a couple of times questions have come up just on the basics of electrolytes. Conventional versus actual flow of current. So, say you have a circuit, and in here, the actual flow is going to be simply from the negative terminal of the battery towards the positive terminal, okay, so in a clockwise direction. Whereas the conventional flow is from the positive towards the negative, okay, and this is the flow that we always follow. Kirchhoff's first law states that the sum of all the currents into a point is equal to the sum of all the currents out of that point. So we can take a point as a junction, and there could be many different loops or routes going in and out of that point or the junction. So sigma I in is equal to sigma I out. So let's have a look at this circuit diagram. And here we've got 3 parallel loops, and the current read by the ammeter A1 is 4 amps, which represents the total current in. And if there is the first loop with a 2 ammeter and a fixed resistor, if that's taking 1 amp of current, we have 3 amps available across the other 2 loops. And let's say the second loop is taking in 1 amp out of that 3 amp of current. The rest of it, which is 2 amp, will be available across the third loop and will be read by the ammeter A5. So altogether, when it all goes back, the current read by A6 ammeter will be 4 amps. So you see the total current in, which was read by A1, is the same as the total current out read by A6. Materials can be classified in terms of how many free charge carriers they have per cubic meter. So that refers to number density. And number density simply states the number of free electrons per cubic meter or in a given volume. This property makes metals the best conductors, followed by semiconductors and then insulators. So, for example, we've got copper, and copper is a conductor where the number density is of the order of 10 to the power of 28 meters, or well, per meters cube. And germanium, whereas, is a semiconductor with a number density of the order of 10 to the power of 18 per meter cube. So you can see that germanium or semiconductors are not as good at conducting electricity because they have fewer number of free electrons per cubic meter compared to conductors such as copper. Now let's talk about mean drift velocity. It is the average velocity with which charge carriers move in an electric field. And these delocalized charge carriers collide repeatedly with the positive ions and move in random directions with random speeds. So their net velocity becomes zero when it's not connected to a potential difference. However, when you do connect the metal wire to a PD, the electrons will align themselves and drift towards the positive terminal of the source. So let's have a look at this diagram here. So in the first instance, the electrons are moving in all haphazard directions and with random speeds. However, when you connect this piece of wire across a potential difference, the electrons will go and align themselves and basically drift towards the positive terminal of the source. Mean drift velocity equation, I equals NAEV, where the symbols have their usual meanings and units, so I'm going to just put them down here. And let's take an example of this diagram here to relate the velocity, the drift velocity, with the cross-sectional area. So say you have a smaller cross-sectional area right here. Now the velocity is going to be much faster because the electrons have a smaller space to wander off to or drift in. So they have more of a streamlined flow, as you may wish to call them. And over here we have got the electrons flowing in much bigger space and area, so they can drift away in many different directions, so the velocity will automatically slow down. So we can safely say that V is inversely proportional to the cross-sectional area. Now coming down to section 2, we will be looking at a few more things, such as circuit symbols, EMF and potential difference, the electron gun, the resistance, and, well, resistivity as well with it, along with power. Here's a list of all the circuit symbols you're going to need. Now, you would have come across all of them except one, that is capacitors. We will not be using this in year 12, but we will be using this in year 13 under the capacitors concept. So please make sure that you do learn all of them for now except this capacitors, alright? Now you've heard of potential difference, but maybe not electromotive force. And just to be careful here, electromotive force is not really a force. It is very similar to potential difference, so let's have a look at the definitions of these two. Potential difference of voltage is defined as the amount of energy transferred by the charge carriers to the different components in a circuit. So V equals W divided by Q. But electromotive force is the amount of energy transferred by the source to the charge carriers. So it's the work done on the charge carriers by the source as they pass through it each time. So EMF or epsilon is equal to W over Q as well. Okay, they both have the same units and they have the both, well, same formulae. However, the definitions are ever so slightly different. Okay, so in this diagram here, the EMF is read by the voltmeter, V, and the electrons receive this particular amount of energy, however much that is. Okay, so say it is 10 volts, okay? So if it is 10 volts, they will be receiving 10 joules of energy, electrical energy per unit charge. And as they go through the circuit and reach the components, they will deliver some amount of this energy to those components, okay, so based on their resistances. So that's what the V1 and V2 will read across the two components here. Let's talk about this interesting concept of the electron gun. Well, electron gun works on the principle of thermionic emission. So what is thermionic emission? Well, it is when a hot filament, metal filament, emits some electrons from its surface, and these electrons are attracted to the anode. And these electrons will gain kinetic energy as they accelerate through this potential difference. And if there is a small hole in the anode, some of these electrons will go through in line, creating a beam with a specific kinetic energy. So let's have a look at this diagram real quick. So we have this setup where there's a hot filament of the metal that's connected to the negative terminal of the source, and therefore it is called the cathode. Now, when this filament gets hot enough, some electrons from the surface will be emitted, and these electrons, being negatively charged, will be attracted or will be accelerating towards this positive anode, and if there is a little hole, the electron with or electrons with specific velocities will pass through and go towards the vacuum. Now, such principle is used in many different things, such as cathode ray oscilloscope, and we may learn about that later on in the course. Now let's talk about energy transfers in this electron gun. And because of the applied potential difference, work is done on the electrons as they accelerate towards the anode. And due to the conservation of energy, this work done is equal to the kinetic energy of the electrons. So W equals E times V, where E is the charge on the electron, and kinetic energy is half mv squared. So if we were to simply combine these two equations, we can say that EV is equal to half mv squared. So this is a really useful equation which is often used in many different multiple choice questions, so it's worth remembering this equation. Otherwise, you can always derive it if you know these two, how to use these two formulae. Let's talk about resistance and Ohm's law. So you guys have heard of resistance before. It is an electrical property of a component that slows down current. And you've also heard of Ohm's law in GCSEs, which states that the current and voltage are directly proportional to each other at fixed temperature. So mathematically we can write this down as V proportional to I. And then we can say that V equals I times R, where R is that proportionality constant, and this is your Ohm's law. The IV characteristic of resistors. Now, as you know, resistors are ohmic conductors, so the voltage is directly proportional to the current at a given temperature. And here's a graph for two resistors, A and B. Now, there are two ways of looking at this graph. Number one is that for the same value of voltage, the current is lower for resistance A compared to B, and hence it will have a higher resistance. Alright, we can say that by just looking at the graph. If we check this out, over here, let's say the value of a voltage, the current is much lower for resistor A compared to a resistor B. Now, the second way of looking at it is a slightly mathematical approach. The gradient of this graph is change in I over change in V, which is reciprocal of resistance, as R is equal to V over I. So the shallower the gradient, the higher the resistance. Alright, so we can see that quite easily from the graph, that the gradient is always the change in y-axis, which is I, divided by the change in x-axis, which is V. So I over V is the reciprocal of the resistance, as resistance is V over I. So basically, if you want to calculate the resistance, it will be the reciprocal of the gradient. Here is another IV characteristic curve for a filament lamp. This is a shape that you guys have come across in GCSEs, and let's just go over this particular graph in terms of the shape and the explanation. So as the potential difference across a filament lamp increases, the current will also increase almost linearly up to point A, but as the current increases further, the temperature of the metal ions increases and they gain more internal energy and start to vibrate faster. So the frequency of the collisions between the delocalized electrons and the metal ions will increase, and the electrons will therefore have to do more work to pass through the wire, which will increase the resistance of the filament. So if you need to calculate the resistance of this filament, simply draw a tangent, find out the gradient of the tangent, and take the reciprocal of it. It's as simple as that. Let's talk about diode. Well, a diode is a semiconducting device that allows current to flow in one direction only, and you have heard of this in GCSEs as well. So here is a characteristic curve for a diode, a typical semiconducting diode, and at A, the resistance of the diode is very high. So with a potential difference in this reverse direction, the diode does not conduct any current whatsoever. However, at point B, the potential difference increases and the resistance begins to drop. And for a typical silicon diode, the threshold voltage is about 0.7 volts, and beyond this point the current increases quite a bit and the resistance drops sharply. And this graph typically shows that diodes are non-ohmic conductors, alright? So what is resistivity? It is an electrical property of a material unique to it. And resistance of a wire, as we know, is directly affected by its length and inversely affected by its cross-sectional area. So we can mathematically write this down as R proportional to L, and R is inversely proportional to A. So when you combine these two, you'll get R equals rho times L over A. Alright, so this is where a new formula of resistance comes into place, where rho is the resistivity, okay? And resistivity increases with temperature, just like resistance. Now, let's investigate resistivity. So here we have a circuit diagram of a variable DC supply with an ammeter and a voltmeter connected across a wire, a given length of wire. So the method is simply set up this circuit and measure the current and the voltage across the wire at different lengths. And for each reading of each set of these readings, calculate the resistance of the wire for recorded lengths using R equals V over I. So in order to calculate the resistivity from a resistance versus length graph, we know that resistance is directly proportional to the length of the wire, so it will be a straight line going through the origin as expected. So we would end up getting a graph like this, where the gradient of this line can be compared to the equation of a straight line, y equals mx plus c, where m will be the gradient, and that is comparable to the formula of resistance, so resistance is equal to rho over A times L. Now let's talk about a thermistor. You've heard of them at GCSEs. What is a thermistor? Well, it is a semiconductor in which the number density of charge carriers increases with temperature, and this is called negative temperature coefficient. Now, just like a filament lamp, it is a non-ohmic conductor, so the current doesn't increase linearly with voltage. Okay, so the temperature increases, it causes an increase in the number density of free electrons. This will therefore increase the current and decrease the resistance. And the graph for the thermistor experiment, here is a circuit setup. So you can investigate how temperature affects the resistance across a thermistor by using this circuit. And you can use an ohmmeter over here, which replaces ammeter and voltmeter to measure the resistance directly. And you can record this resistance values against different temperatures, or if you're using an ammeter and voltmeter, resistance for each set of readings, I and V, can be calculated using R equals V over I. And then you can plot a graph of resistance versus temperature, which looks something like this, as expected. Now let's talk about the light-dependent resistors, or LDR, and it is a semiconducting device in which the number density of charge carriers is affected by the light intensity, and the number density of charge carriers will increase just like a thermistor with the light intensity here, and this will reduce the resistance rapidly, increasing the current. So we've got a... Let's talk about electrical energy and power. Electric power is the rate at which electrical energy gets transferred into another useful form, and there are many different equations of electric power. And power, to begin with, can be written as energy over time, and energy can be written as voltage times charge. So combining these, power equals V times Q over T. So power equals V times I. V is equal to IR, so P equals I times R times by I, and so power equals I squared R. Similarly, I equals V over R, so P equals V times by V over R, so P equals V squared over R. So these three equations will be provided to you in the exam, but they can ask you. When it comes to paying for electricity, we have slightly different measurements. When measuring the cost of electricity, we use energy in kilowatt hours instead of joules. 1 kilowatt hour of energy is transferred when a device with power of 1 kilowatt is used for 1 hour. And therefore, energy transferred in kilowatt hour is equal to power in kilowatts times by the hour. Total cost, therefore, equals energy in kilowatt hour times by the cost per unit, which is... Finally, in the third part, we'll be looking at a few more things to finish off. First one is Kirchhoff's second law, series and parallel circuits, internal resistance, and potential dividers with sensing circuits. We'll also briefly look at potentiometers as it's covered in the textbook, so we'll chat about that in the end. First off, in section 3 is Kirchhoff's second law, which states that the sum of EMFs is equal to the sum of voltages in a closed loop, which is sigma EMF equals sigma V. And let's have a quick look at this diagram here, where we are given that the two batteries, one is 10 volts and the other one is 3 volts, is connected to two components in a series circuit, and the overall EMF is going to be here 7 volts because the polarity of the second battery is opposite to the first one, okay? And so with respect to what's available to the two components, it will be 7 volts. And let's say the first component, which is a fixed resistor, gets 4 volts, the next one will only get 3 volts, okay? And this basically highlights the conservation of energy. All right, so hope that makes sense. Resistors in series. So let's take this simple circuit diagram where you've got current going into these two resistors, R1 and R2, and it has voltage V1 and V2 respectively. So as from GCSEs, you'd recall that current remains the same and voltage is shared. So we can say that V equals V1 plus V2. Therefore, IR equals IR1 plus IR2. And if you factorize the I out, it gives you R equals R1 plus R2. Let's quickly chat about resistors in parallel. So let's say you have this diagram here where there are two resistors, R1 and R2, in parallel, and current I is going in, and there are 2 voltmeters V1 and V2. Now, first of all, the current is added up together, so I equals I1 plus I2. So V over R equals V1 over R1 plus V2 over R2. And we know from GCSEs that in parallel circuits, voltage remains the same. So V equals V1 equals V2, so they can cancel out, giving you 1 over R equals 1 over R1 plus 1 over R2. So this is a really useful formula for resistors in parallel, and although some of you may not have seen this in GCSEs, it's essentially introduced in some of the exam boards in GCSEs, and we can say from here that the overall resistance in a parallel circuit ends up decreasing, and it's lower than the lowest one of the resistors. When a source has some resistance of its own, some voltage is lost through it, and we can define internal resistance as a ratio of the lost volts divided by the current. And when some energy is lost externally, less voltage is available to the components than the EMF, which is provided by the source, and this is called lost volts. So EMF is essentially equal to Vt plus V lost, where Vt stands for the terminal voltage, and V lost is the potential difference lost due to the internal resistance. So we can say that EMF is equal to IR plus I times R, where the lowercase r stands for the internal resistance. And let's have a quick look at this diagram here, where if the internal resistance of this source is 2 volts, or rather 2 volts are lost through the source, then the available voltage to the fixed resistor will be 4 volts, okay? So that's how generally it works. Now, sometimes they may tell you that EMF, that the internal resistance of the source is negligible, then we know that whatever is the EMF of the source will be the same as the total voltages across the whole circuit. Next up is investigating internal resistance. This is one of the PAGs, and here is a circuit setup with a variable resistor, ammeter, and a voltmeter across the source, which has a certain internal resistance. So the method is quite simple. You set up the circuit and record the terminal potential difference for different values of the current. This is why we use a variable resistor, which is used to change the resistance of the circuit so that different currents can be drawn from the power source. And we can then simply plot a graph of V against I. Now, once you've gotten a graph of V versus I, you'll notice a couple of things. A, it's a downward slope, and B, it is comparable to an equation of a straight line. So we know that EMF is equal to Vt plus V lost. So if we were to rearrange it to make Vt the subject, we'll get V equals minus R I plus EMF, which basically can be compared to the equation of the straight line, and that's given to you by Y equals mx plus c. Now m over here is the gradient of the line, as we have we have the current on the x-axis and voltage on the y-axis. So that's your gradient, and bear in mind that because it's a negative gradient, the negative sign in front of r will essentially cancel out. And secondly, the y-intercept would represent the EMF of the source. Potential dividers are simply the circuits which divide the potential difference in fraction of resistance. So if 2 or more resistors are placed in a series circuit, the voltage across each resistor will be in the ratio of its resistance. So we can say that if you had V1 over V2, that will be equal to R1 over R2. Let's have a look at the circuit. And in the circuit, we have an input voltage Vin, and the 2 resistors R1 and R2 are connected in a series. And we have a Vout, which we can measure. So the Vout is essentially the fraction of Vin, because the current remains the same, and we can simply say that Vout is going to be in the ratio of R2 over R1 plus R2, the total resistance, times by Vin. And this is a really useful formula to work out the potential difference. Let's talk about the sensing circuits for LDR. Here we've got an LDR and fixed resistor R1 and R2 respectively connected in series, and we know that when the light intensity across the LDR increases, its resistance will decrease along with the potential difference across it, which means that there would be more voltage available to the fixed resistor. And if we were to, say, place a bulb or an LED along the R2, the fixed resistor, in parallel, then the potential difference across it would also increase. And if it exceeds the threshold voltage of the bulb or an LED, it would simply light up. And that's how a sensing circuit for an LDR works. Sensing circuits for thermistors work very similar to those for LDRs. Here we've got two resistors, R1 which is fixed resistor and R2 which is a thermistor, and we have seen that when the temperature across a thermistor increases, its resistance decreases, and again the potential difference would decrease as well. Okay, so this means that again there will be more volts available to the other component over here, in this case R1, and that just basically means that if you were to place an electric fan in parallel to R1, then the potential difference across it would also increase. And if this exceeds the threshold voltage of the fan will simply turn on. Last but not the least, let's cover potentiometers. They come in different shapes and sizes, and this diagram here shows that you can slide the contact between a resistor, which makes it a variable resistor, and you can measure the output voltage using a voltmeter. So a potentiometer is essentially a variable resistor with 3 terminals and a sliding contact. And when the contact moves towards A, the output voltage increases until it's equal to the input voltage. And it is because the voltage increases with resistance as the current remains the same. This is the end of the video. I hope you found this useful, and let me know in the comments below if you would like to see more videos like this, or if I can improve on these videos. And I'd like to cover more theory videos in physics and in chemistry potentially, so let me know in the comments below, and thank you so much for listening.